Okay, so hello everyone. Good morning or good afternoon or evening, depending where you are. Thank you all for joining us for this workshop on ice-ocean interactions. This workshop is organized by JCIOI, the Joint Commission on Ice-Ocean Interactions. That's co-sponsored by IACS, the International Association for Cryospheric Sciences, and IAPSO, the International Association for the Physical Sciences of the Ocean. And this is the second online workshop that we've organized. There was another one 2 years ago in October 2022, which was a great success. So we decided to have another one. And the workshop is entirely online and over several days. And this session, as well as the other sessions with keynote speakers, are all being recorded and will be posted online on YouTube in the JCIOI channel. So before, just to say a few things about our session today. So this is the second session, and the focus of this session is on ice-ocean interactions in the grounding zone. And we have two keynote speakers, Britney Schmidt from Cornell University and Alex Robel from Georgia Tech. And so just wanted to mention that following the discussion, we're going to have a breakout. Following the two keynote speakers, we're going to have a breakout discussion. So we'll talk about that when we get there. And then we have many more sessions. But before we get started, so that people have time to, I see people are still coming in. So just making sure that I leave time for people to join us. I wanted to mention just a few words by JCIOI. So JCIOI is the Joint Commission on Ice-Ocean Interactions, and we have a steering committee, and a lot of members are going to be renewed in the coming months. And so we have a number of roles to help the development of JCIOI and advertise and emphasize the importance of ice-ocean interactions in general. And so if you're interested in helping us, and so feel free to reach out to the current committee at jcioicommittee@gmail.com, or you can also submit your expression of interest via this online form where there's a QR code here. So if you're interested in joining us, please, we'd love to have you involved, so don't hesitate to reach out. Okay, so let's go back to our agenda today. So today we're going to have two talks. The first one is from Britney Schmidt. Britney Schmidt is an associate professor at Cornell University, and she uses a large set of robotic tools and instruments to study the ice on Earth, as well as on planetary icy worlds. And so as part of that job, she was recently in Florida for the launch of the Europa Clipper mission that was just launched successfully. I think it was yesterday. And so Britney is actually flying back home as we were talking. So she sent us a recording of her talk that I'm going to play now. She's really sorry she cannot join us in person, or I mean online, but she was able to share the talk, and we'll be happy to answer questions if you have some. So I think you should all be able to see my screen now. The sound is not super loud, so you might want to turn up. I cannot make it louder than that, unfortunately. So you might want to turn up the volume a little bit to hear the talk. So I'm going to stop talking and start playing the recording. Okay, thank you.
All right, hello everyone. Sorry I can't be there today. I'll share a little bit about that in a moment. So I'll be kind of discussing the work that we've been doing with IceFin in Antarctica and comparing across multiple different ice shelves. So this is work that I've done together with Peter Washam, Justin Lawrence, Peter Davis, and others. And we'll hopefully highlight a little bit of work that we recently did with the Norwegians, led by Tori Hatterman at NPI. So the reason I'm not there today is because we are sending a spacecraft to the ultimate ice shelf. So we're headed out to Europa as of yesterday. Very exciting times for all of us on the mission. So we had a successful launch, but then that wreaked havoc on travel plans. So anyway, I look forward to working on ice-ocean interactions on other planets in just a short 6 to 8 years. But moving on, back to Antarctica. So the work that we've been doing and that I'll share today is coming from the Ross Ice Shelf. So the very back at Cam Ice Stream, this part of the ice shelf. So about 750 meters thick at the grounding line, and the region that we were studying was about 600 meters thick. We'll also compare that to Thwaites Glacier, which is in a completely different regime in West Antarctica, much more out of equilibrium. And then finally, just touch on what we've done most recently at Fimbalisen. So this is IceFin. IceFin is a robotic underwater oceanographer. And so we've basically got an ROV with some AUV capabilities. And this vehicle, mostly what for the purposes of this talk, will really focus on what's up front, which includes CTDs, dissolved oxygen sensor, cameras, and this forward-looking sonar. But there will show some data that comes from a bathymetric sonar as well, that's here in the midsection of the vehicle, and the altimeter that's in the back of the vehicle, as well as our Doppler velocity logger that gives us the ability to track currents like an ADCP, as well as the vehicle process underneath the ice. So let's compare these two regimes. Since we're focusing on ice-ocean interactions of grounding lines, we've really gotten a chance to compare these very, very different regimes between the Ross and Thwaites and now Fimbalisen. So in the Ross Ice Shelf, we're talking about something that's in basically thermodynamic equilibrium. It's very, it's relatively unaffected by circumpolar deep water. And so we expect it to be behaving perhaps as a healthy ice shelf, or at least as a quiescent ice shelf. And so in 2019, we sent two vehicles out, one out to Cam in collaboration with Antarctica New Zealand. So Christina Holby's team and Hugh Horgan's team out there, also Craig Stevens. And so one of the teams took IceFin out, and we worked very near the grounding line of Cam. And so this is that data, which is coming from Justin Lawrence's 2023 paper. And what it's showing is all of the data from the vehicle. So we're here at the back of the Ross Ice Shelf at the Cam Ice Stream, about 5 kilometers or so. I guess we've got about 5 kilometers from the grounding line. And so this is a track line heading towards the grounding line. These dotted lines here are the vehicle track, and each of these insets is an image, or in this case, a sonar image of the ice or the seafloor. And so I'll point out a few things. One is that we resolved crevasses that actually weren't even really seen in the radar. So probably these are being healed, which we'll talk about in a moment. But what you'll notice in the textures of the ice is that there's this kind of elongated, but still kind of cuspate texture to most of the basal ice, or so most of the ice at the base of the ice shelf. There is some basal ice remaining, but relatively little in this region. And then as you get into this crevasse that we explored with the vehicle, you actually see this transition into a more kind of round, kind of golf ball-like texture, this kind of classic kind of look for three-dimensional turbulence melting the ice shelf. So we see visual as well as thermal indications of this ice-ocean interactions. And so in this region, these are contours of thermal driving. We have just over 0.25 degrees of thermal driving. So it's really, really cold, not a lot of heat, but you can also see that there is a little bit of an overturning current where we've got this warmer, slightly above the freezing point, water in the bottom part of the column, and a little bit fresher, a little bit colder water in the top, indicating the presence of those ice-ocean interactions. And so it's behaving exactly as we might have thought. And we can see the history of this ice stream. I should mention Cam isn't actually moving anymore. And so this really, the seafloor gives us a history of the liftoff of the ice shelf, and then the slow melting back of the ice shelf and stretching of the ice shelf as it goes. It's kind of what we're recording in here. And as I mentioned, we had a chance to explore inside the one of the crevasses. And what you see, this is at the bottom of the ice shelf. You see this kind of pockmarked surface, that's melting features. As we traverse up the inside of the crevasse, as we get to basically the horizon where the supercooling could actually begin, you see a difference in the ice surface. And so here we actually have some accretion of marine ice going on. So right as we make that transition between where there's some amount of heat for melting and actually now crossing the supercooling, we actually see this formation of marine ice. We've got this kind of almost rounded, perhaps barnacle-like texture happening in the upper part of the crevasse. And on the south side, there's a kind of a similar story, but the supercooling horizon is a little bit higher. And then the structure of the crevasse wall actually shows some evidence for brine drainage, creating melt features into the wall. So we've got accretion at the top of the crevasse, and we've got melting happening along the walls of the crevasse in a couple of different regimes. So it's really exciting because the thermodynamics and the ice-ocean interactions are behaving kind of as we would imagine, kind of three-dimensional turbulence down here, and then this erosion of the wall through brine drainage. So in Peter Washam's most recent paper in 2023, he showed in kind of really beautiful detail what's happening inside this crevasse. So not only is the crevasse acting as, you know, kind of a conduit of water where we've got this overturning circulation, which you can see in this leftmost plot, there's kind of a circulation up and over. Turns out there's also a cross crevasse water transport. So it's really complex, and we can see that that overturning circulation plus the cross or down kind of across the grounding line transport of water is affecting those different ice-ocean interactions on either side of the crevasse. So on the right wall, we've got this kind of three-dimensional structure until we start to reduce supercooling. On the left wall, where this downwelling of all of the brine rejection is happening, that's probably what's causing this different structure and the kind of more eroded wall to the south of the feature. So this is showing the current speeds as well as the thermal driving in the environment. And so we can kind of see that kind of overturning and corkscrew transport of water. So that primary flow through the crevasse is kind of in this kind of southward jet that's along the grounding line. And then there's this overturning circulations that's driving water to the south side of in this figure to the left side of the crevasse. That's controlling some of the geometry. And the point here is that most models of these interactions actually don't have this in them. So let's transition over to a warmer-based glacier. So to Thwaites, right, completely out of thermodynamic balance. We're losing lots of ice in this environment. So we've got a really very different story. So you remember, we still saw some crevasses. We saw some ice-ocean interactions. Well, here the kind of ice-ocean interactions are really going gangbusters. What you can see at the from the vehicle data here, so this dotted line is again the vehicle track. These colors are contours of thermal driving. And what you'll notice is that we have more than 2 degrees of thermal driving, right? 0.25 degrees in the CAM case, and it weights more than 2 degrees of thermal driving, at least in the lower ocean column. Even up close to the ice, it's incredibly warm with a lot of heat. So we actually are seeing the ice shelf being eroded by this warm water. The difference is that the topography is quite strikingly different. So this profile here, if you look at the kind of jagged face, and these are crevasses here, those are actually from the altimeter on the back of the vehicle. So we get the seafloor from the DVL as well as from the bathymetric sonar. But on the ice-ocean interface, we can actually map with the altimeter in the back of the vehicle. And so what it's really showing are these really obvious staircase effects. So they're what we call terraces, and those are distributed uniformly across the grounding zone region. And they progress. Close to the grounding line, they're relatively disorganized and kind of starting, but not as organized. And by the time you get maybe a kilometer from the grounding line, they're very, very regular, extremely flat tops, extremely steep sides. And this really matters for the ice-ocean interactions happening in the region. So we look up inside of the crevasses here and look at a couple of terraces. What we notice actually is that the lateral transport of heat, so the amount of heat that's available to get to the walls of the crevasses or to the walls of these terraces turns out to kind of be the driving force here. So what we're showing in this left plot is that the fastest moving water, as well as the warmest water, is making it to the wall of this crevasse. And so that's actually driving melting, driving the widening of these crevasse features. And that's true both of crevasses and of terraces. And so this topography is kind of being driven or eroded actively by lateral transport of heat. So this is showing kind of 2 perspectives of a sidewall. It's got that 3-dimensional scalloped texture that indicates 3-dimensional turbulent melting of the ice shelf. but these are very, very steep interfaces. Whereas when we get to the bottom of such a feature, it's incredibly flat. So there was nothing observed in the CAM data that looked anywhere close to this. So very, very flat, very, very steep sides is what's being eroded. And it's true of both crevasses and of these terraced features. Just kind of showing a couple of up close views of those scallops, and then this contrast between the flat base of this terrace or this crevasse and the sidewall. So what's happening inside the crevasses is kind of the same here. Actually, it looks like the crevasses are also acting as a long or a kind of a long grounding line transport. So while we've got some inward flow of the ocean water towards the grounding and some outward flow, most of the circulation in both regimes is actually along the coast. And the crevasses are transporting water, it looks like, in the opposite sense. And so we've got strong lateral flow inside those crevasses. So along with this story about, at least in the case of Thwaites, about the lateral heat transport, that's what's actually kind of causing this interesting stair-step features to form, not just the ice shelf base, but within the crevasses, and in fact, widening them out. So this is showing the current speed. So relatively slow current speeds, but enough to actually drive a lot of transport of water across the grounding line regime. And so those crevasses really do look like they're acting kind of as funnels for water transport. So altogether, what that's showing is that this is kind of a different interaction style than we saw at CAM. There's no evidence here for any healing or any production of marine ice in the top of the crevasse. In fact, what we're seeing is extremely strong melting down vertical faces. So these are the melt rates, at least 30 meters per year inside the crevasses that we observed. And then also very, very high melt rates on the edge of these terraced features. And so that lateral transport of heat is actually probably widening features so that we have this lateral melting as opposed to just vertical melting. What we also observed in detail was that the production of some meltwater is actually suppressing some of the vertical melt in this region. And that's covered both in our paper about Thwaites as well as in Pete Davis's paper. So just kind of highlighting the difference here is that stratification that's produced by having lots of fresh water is suppressing what we would expect to otherwise be extremely high basal melt rates. So it's making it less, but inside the crevasses, because the water is flowing back up to the top, the more buoyant meltwater, and then being transported along the crevasse, we just see the heat making it to the sidewalls. And so it's kind of this dichotomy in the ice-ocean interactions. So I'm going to show you Fimbalisen, which isn't actually at a grounding line, but the important thing is that it is inside of a channel. So we'll show you some data from that. And the interesting thing about Fimbalisen is that it is neither in the very cold regime that CAM is in, nor is it in the extremely warm regime that we find Thwaites in. And so it's kind of in this dynamic region. And there's indications that that there may be kind of changes over the season in what type of water and what thermal forcing these environments are seeing. And so it's a kind of an important place to study because it's kind of between this kind of cold, very relatively stable environment and this really out of balance one at Thwaites. So last season we went out with the Norwegian Polar Institute led by Tora Hatterman, as I mentioned, and got to get inside of a subglacial channel in that environment. And so what I'm showing here is just very preliminary results of the thermal driving on the left-hand side, salinity in this center panel. And so we're showing kind of a similar thermal environment, I guess, to CAM ice stream, but we've got a little bit more heat through most of the water column in that area. So inside the crevasse, what we can see is it's relatively steep sided, but it's actually, inside the channel, not so steep as the crevasses that we observed, but also kind of guide your eye over here where we can see some terracing forming as well. So this kind of structure is we've got terraces forming a little bit higher on the downflow side, and on the upflow side, we've got them happening a little bit deeper. So kind of indicating a little bit different regime from one side of the channel to the other. If we look at the dissolved oxygen sensor, we can also see that that's some indication of melt. We actually did get up into this top part of the channel where we see some accumulation of the meltwater that's being produced in these features. But we can look at the ice ocean interactions as being kind of really different across the channel regime. So here in this image to the right, what you're seeing is this very transverse kind of ridging. So the ridges are perpendicular to the direction of current flow. And so across the top of the channel, we're seeing these ridges forming perpendicular to the direction of the water flow, which is kind of interesting to see. Along the bottom of the ice shelf, we're still seeing scalloped features like we saw at CAM ice stream. So it's not the strong kind of flat and then it's kind of flat base and steep wall that we saw with the ice ocean interactions happening at Thwaites. But there are places inside the terraces on these very flat walls where we do see that. So it's kind of a mixture of this terrace behavior and the kind of more three-dimensional topography that is being seen at CAM. So we've got kind of this dynamic interaction. One of the questions we have is this forming in the ocean right now? Or perhaps was this kind of terrace structure actually inherited from when the channel was further upstream, closer to the grounding line, deeper, perhaps exposed to warmer water? So anyway, one of the things that we're working on, so Peter Washam's been putting this together, is to look at the velocity structure inside of the channel. So more on that later. Mostly uniform, but it does seem that there's some kind of detail, especially going down the sides of the crevasse. So we're still working on that. So work in progress. So just quickly, just to end, I wanted to just comment on these kind of modes of interactions that we're seeing. So I think the crevasses are a really nice story that show how different these environments are. So in CAM, the Ross Ice Shelf, right, basically thermodynamic balance, where we've got three-dimensional turbulence is seen everywhere. It's seen on the base of the ice shelf. It's seen along the sidewalls of the crevasse. And then up in the top, we've got this reaccretion, this formation of marine ice at the top. In the middle, we've got Thwaites, which is this out of balance, very warm regime in which the kind of trade-off between lateral melting, vertical melting from the warm water and the stratification that's produced by that is causing this very different style of ice ocean interactions to take place, where the predominant melting is perhaps along more vertical features, and those vertical features are formed by the melting being so rapid at the grounding line and then progressing outward. And finally, in Fimbalisen, we've kind of got this mix of those two modes that we're trying to figure out. So we're looking forward to being able to say more about this. So that, again, that kind of other important part about it is that at least for these crevasses near the grounding line, it looks like they're actually transporting quite a lot of water. And so cross grounding line or along grounding line transport of water is going to be important for those crevasse features. And so finally, this is work that Peter's been showing. So what's the forward-looking perspective on what we might do with this information? Well, we really need to understand the space in which these very detailed observations might make it into modeling parameters. And so our kind of thoughts on this at the moment is that it's not that we need to be able to actually model these kind of meter scale interactions, but in fact, just to know what regime we're in. And so some combination of the current speed and the thermal driving in the ocean gives you kind of the relative importance of these different modes of melting. And so if we can kind of make an educated guess about what regime these features or different parts of the grounding line might be in as a function of where they are geographically, then maybe we could get to a place where at least we could represent the melting in a more realistic way, as opposed to this standard, overturning shelf circulation, buoyant plume type of modeling that has dominated most of the grounding line models. What we can say is that is certainly more complicated than just simply thinning the ice as a result of undercutting by circumpolar deep water. And I think, so this kind of way that Peter's trying to represent it here as a function of drag coefficient, as a function of buoyancy, as a function of this importance of stratification. And then the current speed is a really important story, because we think that as the current speeds increase, this ability to have the stable stratification dominating the heat transport will probably be going away. And so as the current speeds increase, you have less and less a chance for that kind of meltdown. But that's just hypothetical. So we'll see whether we find that the next time we get out to a grounding line. So yeah, so a few things common across both systems is we've got this along flow crevasse transport of water. There's not a lot of three-dimensional or two-dimensional overturn the way it has been modeled previously. So it's kind of this corkscrew method or corkscrew process through the crevasses. Some dissimilarities between these regimes are just this difference in the mode of ice-ocean interactions, whether it's three-dimensional or two-dimensional, are actually suppressed by stratification. And so that's got to be a really important part of the story. And so at what point in time you end up back into that three-dimensional turbulence versus this stratified environment, I think is a function probably of current speed as opposed to just of ice shelf topography. So more to do. And just in closing, I wanted to thank everyone that's helped us to do this work. Thank everyone here for listening. Sorry, this is a bit rushed, and I really apologize that I'm not able to give the talk live, but I hopefully Peter and Veronica, who are folks working on the data actively, might be online to add to the conversation and answer a few questions. So with that, I'll say thank you and bid you farewell from the Atlanta airport.
Great. I guess we give a virtual thanks to Britney. And I think what we'll do is, so I see that Peter is here, but perhaps what we'll do is, if you have any questions on Britney's talk, maybe you could put them in the chat and then Peter can answer them, or what we'll do is move on to Alex's talk and then have a bit of a discussion at the end on both of them before the breakout discussions. So that will give a chance for you to think of any questions and then also post them and potentially for Peter to respond if he is available. And Veronica, I can't see, but maybe, yeah. Great. Okay, well, in that case, I think, yeah, we'll move on. So next up, we have Alex Robel, who is an associate professor at Georgia Tech in the School of Earth and Atmospheric Sciences, where he leads the Ice and Climate group. And he will be talking to us about his recent work on modeling seawater intrusions and melt underneath grounded ice. So, okay, great. Thanks, Alex. I can see your slides fine. So take it away whenever you're ready. Thanks. Oh.
All right. Can you hear me? Okay, great. All right. Well, thank you all for inviting me. I'm trying to now move my, sorry, hold on one second. Oop. Get my face out of the way. I am, as always, very honored to go after my former colleague, Britney Schmidt, in talking today. And so I'm going to sort of take over from where Britney left off, talking about all these wonderful and unprecedented observations of the area of the ice shelf very close to the grounding line. And what I will be doing today in sort of the spirit of the keynote is talking a little bit about some work that me and some collaborators have done over the last few years, but also really kind of just reviewing where we are as a community and thinking about seawater intrusion past the grounding line, right? So all of these warm waters that Britney was just talking about, you know, whether they're getting past the grounding line and what happens when they do. So to start with, I just want to kind of give a cartoon to really put us in a location and get you thinking about this problem if you haven't thought about it before. The problem that we're thinking about is at the junction between the glacier, the glacier ice, the ocean, and the solid earth beneath, right? So this might be the grounding line or the terminus if you don't have a floating ice shelf. You know, typically in a thawed bed case of an ice sheet, we would think there is some amount of fresh subglacial discharge occurring from underneath the ice sheet, which is then moving into the ocean and then potentially creating a plume. And really the question that this talk gets at, and a lot of the work that's been done in the last decade or so on this problem, is really what happens at this interface between fresh subglacial discharge and seawater. And does any heat from the ocean, which generally speaking has a lot more heat content than the fresh subglacial discharge, does any of that heat content from the ocean find its way upstream of the grounding line? And so what I'm going to start with is sort of this question of, well, what happens if it does, right? And why is this problem important? So looking at this plot, scrutinizing this plot, which is from a intercomparison project of ice sheet models that was organized by one of our conveners, Hélène Sorossi, about 5 years ago, or published about 5 years ago. Thinking about this plot and the outliers in this plot is really part of what got me thinking about this problem. And so what you're seeing here is each bar in this bar chart is a different ice sheet model or configuration of an ice sheet model, and its contribution to sea level rise at 2100, given some the same change in basal melting underneath floating ice across all the different models, right? So models make a lot of different choices about how to think about basal melt and what sets the basal melt rates. We heard a lot about that yesterday during the parameterization session. But what this plot shows that I think is really lovely in particular is that there's a few models and model configurations that are outliers in terms of the predicted response of the Antarctic ice sheet to basal melting. And a really nice experiment was done with one of these models. This is the New Zealand version of PISM. And they did 4 runs with this model. And in 2 of the runs, that is the red bar and the black bar, they allowed melt to occur on mesh elements of the model that included the grounding line. So that's kind of like this bottom situation here where each triangle is a mesh element of your ice sheet model, and the blue is where the ocean is, and the brown is where the ice sheet is, or where the grounded ice is. Right. And so the bottom is one way that you could do this, which would be to interpolate melt in some way. This also is a great graphic from another wonderful paper of Helene's from 2018. And then the top is how a lot of models currently handle this issue, which is basically that they just don't put any melt on mesh elements that include the grounding line. And so basically with this exact same model, with everything else being equal, if the only thing that you do is you allow melt to occur up to the grounding line or upstream of the ground, a little bit upstream of the grounding line due to sort of numerical approximations of where the grounding line is, then this increases the contribution of the Antarctic ice sheet to sea level rise by 50 to 100%. Right. So this relatively small knob that is really just about sort of the numerics of the model has a very big impact on the sort of projections that we make of Antarctic ice sheet change. So that's one reason why it's important. Another one is that using the same model, this group from Wellington, led by Nick Gollage, did some experiments to see whether they could explain the potential sea level contribution suggested by geological observations of the contribution of the Antarctic ice sheet to sea level rise during the Pliocene warm period, right, when global atmospheric temperatures were about 2 to 3 degrees warmer than today, right? So this is typically used as an analog for where we might be going in the future. And during that time period, global sea levels were probably anywhere from like 5 to 15 meters higher. And so basically what they showed is, again, when you turned on this allowed melt to occur just up to the grounding line and potentially a little bit upstream of the grounding line, you got several meters more melt of sea level contribution from Antarctica. So in all of these models that I've talked about so far, these are ice sheet models that are relatively coarse because they're being run over very long time scales or over large areas. And so what we wanted to do, so this is a paper of mine, Earl Wilson, and Helene Sorossi from 2022 in the cryosphere, and I'll talk a little bit more about this paper later in the talk. But what we wanted to understand was if we had a very high resolution ice sheet model, so in this case, we're talking about 250 meters resolution everywhere in the domain in the experiments that I'll talk about on the next slide. If all we did was we allowed some basal melting set by the ocean basal melting rate upstream of the grounding line over some distance, how much would that change the sensitivity of the model? So kind of asking the same question as before, but not asking the question of, this numerical artifact of melting upstream of the grounding line. But if we put basal melting upstream of the grounding line on purpose, how much would that change the sort of predicted sensitivity to ocean forcing? And so we added this very simple parameterization to ISSM. And all we did was we prescribed the distance over which basal melting falls off upstream of the grounding line, if the dashed line here is the grounding line. Okay, and so we did this in sort of two benchmark experiments. One is a sort of well-known benchmark. It's an idealized sort of marine terminating glacier from the MISMIP-1 suite of experiments. It's called ICE-1R. And so what you're looking at here is a plot of the volume loss in this ice sheet model experiment after 100 years on the y-axis in cubic kilometers, and as a function of the distance over which basal melting falls off upstream of the grounding line. So the black dot in the top left corner is if there is none of this sort of intrusion-based melting upstream of the grounding line. And then the colored dots are the amount of volume loss that you get over those 100 years if you allow hundreds to thousands of meters of intrusion and melt upstream of the grounding line. And basically, we get kind of a similar answer, which is that you get an increase of about 30 to 100% of volume loss from this idealized marine ice sheet, which is sort of equivalent to doubling or tripling the melt just under the floating ice. And so it's a very important knob for potentially increasing the sensitivity of ice sheets. And we can do the same thing with simulations of Thwaites Glacier, and you'll find similar results. Okay, so I hope I've convinced you that this is important. Now, of course, the question is seawater intrusion upstream of the grounding line a thing that is happening? And where I want to kind of start things, because I think, when I talk to folks about this, there's kind of this inherent idea that we're sort of like, pushing this, this hypothesis or this idea as being definitely true and the solution to sort of all of our problems in ice sheet modeling. And that's not really how I think about this problem. The way that I is a hypothesis, and our job as scientists is to potentially falsify that hypothesis. And if we cannot falsify this hypothesis, and if we deem that it's plausible under certain circumstances, then our role is to constrain, exactly how important or under what conditions this intrusion could occur, right? So that's kind of, my starting point in thinking about this problem is, seawater intrusion is a thing that could happen in theory, based on what we know about how estuaries work and, how grounding lines work. And can we roll that out as a possibility underneath ice sheets? If not, under what conditions would we expect it to occur? Okay, and so this idea goes back about a decade. It goes back longer than that, but I think there was a pair of papers in 2013 by Ryan Walker and Roy Sayok and Gray Worcester, which focused on this question of whether tides could be pumping water upstream of the grounding line. And I think generally the answer was that yes, they could be, but that it would be relatively limited in terms of how far tides could pump water upstream of the grounding line. And more broadly, what they were doing was they were thinking about this as a one-dimensional problem where freshwater underneath the ice sheet and seawater in the ocean, the density differences between them were not really considered, as part of the problem. And so this is really where Earl Wilson's work came in 2020, and this is what got me interested in this problem. So Earl had this wonderful paper in the Journal of Fluid Mechanics in 2020. This image in the back is from that paper. And basically what this paper laid out was a series of experiments. And so in this image, you see kind of what the experiment is doing. Basically, you have a pipe that is where fresh water is being discharged through the pipe, and then it exits into a basin of seawater. And that's what's on the right end of the figure over here. So the dark blue fluid here is sort of fresh subglacial discharge, and the transparent colored water is seawater. And so, of course, in these experiments, as you know, probably about 100 years of theory and experiments and observations on estuaries would bear out, you will get this intrusion of the seawater underneath the freshwater. And that's just simply because seawater is denser than freshwater. And so in this paper, they also lay out a theory for this problem. And in the theory, they consider a confined subglacial channel. And so this is where I got interested in the problem. And Earl and I started talking about this along with Helene. And what we did was we sought to take their theory from the 2020 paper and to generalize it. To generalize it to sort of a wide range of potential subglacial hydrological configurations that you could imagine, either with hard beds or soft beds. And to think about, you know, different conditions that you could have in terms of the slope of the bed, in terms of the speed of fresh water coming out, and you know, some other factors as well. And so what we did was we wrote down basically a 2-layer shallow water equation. This is similar to Earl's original model, but we allowed for the possibility that you could have unconfined flow underneath the ice sheet, and that you could have macroporous sort of obstacles impeding the flow of water. And so if you just take this model at steady state, you assume ocean currents are relatively slow compared to fresh subglacial discharge, although that's not a critical assumption. You can basically solve for a closed form solution for the intrusion distance that you would expect. I see some things coming up in the chat, but if I'm going over time, please someone just shout at me. Okay, so basically this provides a closed form solution, and what this closed form solution tells us is that to first order, intrusion is controlled by this length scale. That's what I have here on the right. This is this L tilde. And this length scale of intrusion is basically set by the height of the subglacial gap, whether that's a channel or a water sheet or some macroporous hydrological system. So it's that gap height H. And then the rate of discharge of fresh water from the interior of the ice sheet. The drag of water against the bed and against the ice also plays into this problem as well. Okay, and so this is basically the I guess our solution, or our conclusion from this study is that if your bed is retrograde, if the subglacial water gap or the subglacial gap is relatively thick, that is to say order centimeters or more, and the discharge rate is low coming from the interior of the ice sheet, you can have intrusion over hundreds to thousands of meters upstream of the terminus or grounding line, right? And so this is basically the theoretical prediction for hard-bedded ice sheets. So what we found in that study, which is kind of more of a sub point or a separate point, is that we really don't expect seawater intrusion to be that important in subglacial sediment. And that's just because the permeability of subglacial sediment is relatively low. And so you shouldn't expect to get very much intrusion in those cases. Okay, so that was kind of the starting point. And I think really one of the things that's exciting about working on this problem is that there's been, I think, a lot of excitement and enthusiasm in the community about continuing to push the ball forward on this problem. And again, I think really coming from the standpoint of, again, this is a hypothesis. We need to understand kind of the constraints on this hypothesis, where we expect it to be important, where we expect it not to be important. That we published in 2022, I think, you know, started to maybe define the bounds of what are the circumstances where we expect intrusion to occur or not occur. And so this was then continued in this great paper by Alex Bradley and Ian Hewitt, which was published earlier this year in Nature Geoscience. And they basically, starting from our model, they basically added in this idea, right? Which, if you look back at the theory that I just talked about, basically it says that you get more intrusion if the subglacial gap height is larger. And if we're saying that the seawater is bringing heat with it, and that is melting the ice, which should increase the subglacial gap height, then this is basically going to constitute an extra positive feedback that wasn't present in our original model, because in our original model, we assumed that the geometry of the subglacial gap is constant in time. And so they add in this positive feedback, and they add in a sort of model components of the model for the evolution of the subglacial gap height as a function of space and time. And what they found is that basically this increases the range of scenarios in which we expect intrusions to be either important or unbounded. Now, the question, there's an interesting question about whether unbounded intrusions should be expected in reality, and I'm happy to discuss that maybe after the talk. But basically what they find is that this basically increases the range of conditions in which intrusion is important and expected to bring ocean heat upstream of the grounding line. And so you can look at this in terms of a parameter space that's sort of orthogonal to the parameter space that I showed, because now they're including this melt rate, which we didn't include in our model, where there was no melting. And it adds this very interesting new dimension and perspective to this problem. Okay, so far I've been talking about relatively simple shallow water models for seawater intrusion. My student, Madeline Mamer, who I think actually might have talked about this 2 years ago at the last one of these workshops. She has been looking at this problem. There's a lot of questions that can be asked and have been asked about this work in terms of many of the simplifications that we make in order to get to a closed form theory. And so she really kind of has taken it from that point and looked at this question of intrusion within a high fidelity CFD solver. So this is an ANSYS Fluent, which is a commercial fluid dynamics solver package where she's simulating water flow in a similar geometry to what I just showed, but at a resolution of about 1 millimeter in the model. And she asks 2 questions. One question, well, a number of questions, but 2 of the questions that I'm going to highlight here are, what is the role of turbulent mixing? So this model includes a turbulence closure scheme, a K epsilon turbulence closure scheme. And that turbulence closure scheme has a parameter in it. And we use that parameter as sort of a tuning knob to basically determine whether the strength of turbulent mixing plays an important role in setting the intrusion distance. And nominally, her conclusion, which you can see in her preprint, which is up on the cryosphere now, and it's under review, that turbulence doesn't seem to be playing a strong role in setting the intrusion distance. What does seem to play an important role in setting the intrusion distance is the feedback that melting has. So she doesn't include the change in the subglacial gap geometry, but because that's not possible in this model. But what she does do is she asks the question of, how does the generation of meltwater affect the fluid mechanics? And basically what she finds is that it suppresses melting due to suppressing near ice temperatures in the model. So that's interesting. And then what she also does is she compares what the model predicts for the melt rate, right? So again, in this model, we're able to resolve the temperature 1 millimeter away from the ice. And so you can kind of directly calculate the melt rate. And what she finds is that if you compare it, so the solid red line or maroon line here is what her model predicts. And then the red dots here are what a 3-equation parameterization, shear-driven parameterization for melting would predict for the melt rate here. And that in general, we find that the melt rate is much higher than it would be, or than it would be predicted by a shear-driven parameterization. Okay. So that's wonderful work that's currently in review, and you can go look at it now. There are some other wonderful papers that have come out in the last few years from the group at UC Irvine and others collaborating with them. So this one in particular I'll highlight, ask this question of whether you can explain in an ice sheet model, whether you can explain or reproduce the retreat of Petermann Glacier in Greenland over the 2010 to 2011 time period. Basically what they conclude is that if you add melt in a 3 kilometer long intrusion into the model, that is sufficient to explain the recent retreat of Petermann. If you don't include that intrusion-based melt, you can't explain the retreat, or you cannot reproduce the retreat of Petermann over these last 10 years. I would say it's probably the case that this is a sort of sufficient but not necessary sort of condition. But it is sort of starting to point the direction again that intrusion provides that necessary extra sensitivity to reproduce a number of different kinds of observations, whether that's from paleo contexts or modern contexts. There's a lot of really interesting observations. Brittany just talked about wonderful observations, so I'm not going to talk about that at length. But there's been really great work with INSAR showing evidence for tidal motion upstream of the grounding line at Thwaites. Also terrestrial radar interferometry in Greenland, also showing evidence basically for water being trapped upstream of the grounding line. And actually very close to the observations that Britney was showing from the CAM ice stream grounding line. There's a wonderful study by Aaron Whiteford from a few years ago showing basically this channel, this basal channel that cross-cuts the grounding line at CAM ice stream and is basically incised about halfway through the thickness of the ice sheet there. And so what they conclude in this study is that the melt rate in this basal channel upstream of the grounding line is 35 meters per year, right? Which is not a melt rate that we would expect to see purely due to subglacial discharge alone. And it might be some indirect evidence that there's some intrusion occurring through this channel. Okay, finally, I just want to plug some exciting new work that's happening here at Georgia Tech through a collaboration with a colleague of mine, Chris Lai, in civil engineering. So Chris is an experimental fluid mechanics person. We have this 4-year NSF grant to basically what him and his grad student did was built a ice ocean interface in the lab in a flume, and they created a plume underneath it. So I'm going to just show this animation here. So the plume, in this case, the plume is coming underneath because this is more of a sort of traditional Greenland-like plume. The left-hand side here is real ice that's manufactured in the lab. And what they're able to do is simultaneously measure velocity, temperature, and salinity in this interface, also across the entire boundary layer at sort of accuracies or at resolutions of less than a millimeter, right? So basically what this allows you to do is sort of recreate a lab-scaled version of a subglacial plume or a proglacial plume moving up an ice face, and to then measure the properties of the boundary layer and also the melt rate that it's producing, right? And so the next goal is basically to this whole ice block and this whole apparatus can be turned on its side, and you can do the exact same thing for a more intrusion-like interface, right? And so the other exciting thing about this apparatus is that it's long enough that you can basically observe the complete transition to turbulence over the course of the flume while measuring it the whole way. But it's small enough that you can put it all inside of a cold room as well. So exciting work. None of this is published yet, but you should probably be seeing papers coming out about this starting in the next year or so. Okay, so I just want to end on some open questions that I think this is certainly not an exhaustive list, but these are some of the questions that I've been thinking about and sort of thinking about the seawater intrusion problem. And that is what role, so from a theory and modeling perspective, none of the sort of theoretical or modeling studies that have been done thus far really in any way simulate dynamic subglacial hydrology. And so it's really interesting to ask this question of if we combine these relatively simple models that we've been working with a lot of the wonderful theoretical work that's been done on subglacial hydrology and the evolution of subglacial channels and water sheets, what role does that play and those dynamics play, creek closure, these sorts of things play in setting the channel geometry. So I think that's an interesting and open question. Thinking about large scale models, right? The challenge here is I'm talking about, simulating this process in a very high fidelity model using millimeter scale resolution. And obviously that's not going to be possible to do in a large scale ocean model with, resolutions of order meters to hundreds of meters. Right. And so is it possible to develop a basically vertically average theory of intrusion that does not require you to resolve the entire channel, at high resolution, in order to couple models or provide some sort of intermediary between an ocean model and a subglacial hydrology model, right? And so in thinking about coupling those two together and what kind of melt rates you would predict for those, right, is there sort of an intermediate model that we can produce that would help us to understand this process and ultimately to put this into our coupled ice sheet ocean models. I'm really excited. I'm glad that they put me right after Britney's talk because obviously there's a lot of really exciting observational tools that are now coming online. And I actually think, so I showed a few observations. Those were all relatively indirect observations that suggested that seawater intrusion could be occurring upstream of the grounding line. Are there more direct ways that we can measure intrusion, right? Ice fin is agile enough. Could it be going into a subglacial channel? I think these provide interesting possibilities for future field expeditions. And then also, ground-based platforms for measuring basal melt rate at high accuracy, like AP-Res. Could those tell us, a more detailed story about how basal melting is changing across the grounding line? And then finally, what does this mean, for the gap between contemporary models and models of high sea level high stands in the past? Again, I don't think anyone should go into, working on these problems with the idea that any one process is necessarily going to, totally solve all of our problems as a field and, answer all of these outstanding questions. But what exactly is the role that seawater intrusion plays in closing this gap, in explaining past observations? And of course, then what does that mean for future ice sheet change under warming? So I will leave it here, and I'm happy to engage in the discussion with y'all. Thank you.
Thanks a lot, Alex. That was a great talk and really touching on many interesting points. So thanks a lot. We have time for questions. So please raise your hand or put your question in the chat if you have question for Alex. And also Peter is here and there was already some discussion going on in the chat. So if you have question about Britney's talk, you can also ask them and hopefully Peter can answer them. Otherwise, we'll just forward that to Britney.
I want to start with a quick question for Alex. So with the kind of to what extent does the fresh water in the subglacial system kind of buffer the impact of that saltwater wedge that's denser and underneath it? Is that, I mean, yeah, presumably heat obviously will warm up that fresh water, but yeah.
Yeah, I mean, I think it's a good question, and I think that's sort of where we're going next in some sense, or trying to answer that question exactly, because basically in the sense that Alex and Ian's recent paper talked about this new positive feedback, I think this is probably a negative feedback, and I think it's really just a question of how large is the negative feedback. Ultimately, though, the negative feedback here is the magnitude of it is exactly dependent on how much melting you have, right? So Maddie's work shows that it's definitely reducing the melt rate, right? So basically she does a pair of experiments, one where she simply diagnoses the melt rate without putting that melt back into the model. And so she just diagnoses what the melt rate would be if the melt was basically just happening and then disappearing in some sense. And then she does these experiments, which I showed, which are, what if the melt then actually goes in? And what she finds is basically a reduction in the melt rate by sort of a factor of, or an order 1 factor, right? It doesn't completely eliminate the intrusion. And it has to find this happy medium, because ultimately, right, it suppresses the melt rate, but the melt is the thing that's suppressing the melt rate itself, right? So, ultimately it's going to kind of come down somewhere in the middle. And where it comes down in the middle, I think, is, she's done a few experiments, which are going to be very dependent on a lot of the details in those experiments. So I don't think there's like a general answer yet to that. But something that I am excited about that I would like to work on is this sort of question of, even within the context of these simpler models, like these shallow water models, in Earl's original paper, our follow-up paper, and then Alex and Ian's paper, we all just make the assumption that the amount of melt, the rate of melt, is unimportant for the overall mass balance, or the sort of mass balance of water in the subglacial channel. And it would be interesting and relatively straightforward to just relax that assumption, right? And just solve the whole, you wouldn't be able to get a closed form solution anymore, but you could still numerically solve the problem and start to get a sense for what the magnitude of it is within the context of these sort of simple mathematical models. So hope that answered your question.
Thanks, Alex. I see that there are other questions. First, Becca Jackson. Becca, do you want to ask your question to Alex?
Sure, thanks. Thanks, Alex, for a really terrific talk. So sort of related, although more focusing on the mixing, I was really interested in the result you reported, that the intrusion length wasn't sensitive to the turbulence closure, or the amount of mixing. And I was curious, can you elaborate on that and kind of why you think that is, and how that pretty different than my understanding of like salt wedges and estuaries. So can you speculate about that?
Yeah, so I think that was counter to our expectation as well. And that was, in some sense, the whole point of doing this project and this experiment was, let's actually consider turbulent mixing and see how that affects things. I think there's a detailed answer in Maddie's paper, so I would absolutely encourage everyone to look at that the preprint. It's great thing to dig into. I think the short answer is that the flow rates in general that we're considering. So basically, Maddie considered 3 cases. Let me make sure I get this right. It's order millimeters to centimeters per second of flow. So we're talking about very near laminar flow. And so, of course, there's this question then of like whether using a K epsilon turbulence closure is actually appropriate in that, so, there is that whole question. But basically what you can do with the model is you can also just totally turn off turbulent mixing, and you can just consider a laminar case and just solve the equations under a turbulent or under a laminar assumption. And it gives almost identical results. And so what I think that's saying is that basically at the flow speeds, and the thing that someone's going to ask me next is like, what's the Reynolds number? And I could absolutely not tell you that off the top of my head, but it is in the paper. And Maddie were here, she would know that. But I think at the Reynolds numbers that we're considering, it's just that it's not that important. So.
Oh, interesting.
Now,
okay, thanks.
In Greenland, that might be different, right? But we were sort of operating in a regime that was like more Antarctica-like. So,
thanks.
Thanks, Becca. Thanks, Alex. Roland, you have your hands up if you want to ask your question.
Yes. Thanks very much, Alex. I first want to start with a quick observation. You motivated this initially with these outlier ice sheet models and the way they were treating melting at the grounding line. I mean, I think it's pretty important to highlight that what's going on there is, by definition, you're getting more melting in the vicinity of the grounding line. And it's not surprising that that drives grounding line retreat more efficiently, and that cumulatively leads to the volume change. And my concern at that simple picture of extrapolating the very high melt rates that parameterizations are suggesting at the grounding line into the interior is it doesn't seem to gel with what the physical heat transport is going to be in this very thin layer. So I feel there's a question of the reality of that. The other specific question I have is, we think of tidal flexure as being very important, in particular in those Thwaites examples that you quoted for accessing or refilling or pumping seawater into these regions upstream of the grounding line. So how much does that affect on the gap come into consideration? And again, how much heat is actually getting transported in there?
Yeah, so I mean, those are great questions, and I think that absolutely everyone should be very skeptical of ice sheet models at all times. And I presented that first slide not to say like, this tells us that intrusion is happening, but rather it tells us that ice sheet models care a lot whether intrusion is happening, right? I think that those are sort of different statements. And the rest of the work and kind of the ongoing work really is getting towards all these other thorny questions of, is seawater intrusion happening? Under what conditions would we expect it to occur? What do observations tell us, et cetera, et cetera? I think as far as the heat transport goes, I mean, the answer is that if you can get water that is even a little bit above freezing upstream of the grounding line, it is going to drive some amount of heat flux. Now, of course, the question is how much heat flux, but the point is like what the baseline is, right? In a place like Antarctica, where we're thinking, generally about basal melt rates under grounded ice of the order of millimeters per year to maybe tens of millimeters per year, right? Starting to even think about sort of tens of centimeters per year to meters per year of basal melting, like that would be a very big change, right? And of course, as you said, you're doing it right in the place where it's likely to have the most impact on the sensitivity of ice sheets to forcing, to external forcing. So I think the answer is like, in terms of heat transport, I think the reason why it's such a dramatic, potentially a dramatic change is because even with a relatively small amount of warm water intruding underneath the ice sheet, it drives potentially a lot of heat flux into the ice, right? Compared to the baseline, right? Which is basically just set by geothermal heat flux. And so, I think,
I thought in fast flowing regions, I'm sure the geothermal heat flux is irrelevant compared to the frictional heating.
Yeah, that's right. Sorry, geothermal and frictional heating. But the point being that like, if you can get water even a few tenths of a degree, above the melting point, upstream of the grounding line, that is a lot of heat compared to, and if there is sort of regular recycling of that heat, right? If there's a sort of open communication with the ocean, which is kind of gets to your question about tidal pumping, I think tides definitely play a role in this process. I think there is a broader question of whether tides are necessary for this sort of intrusion process. And I think that's, where basically this estuary-like explanation says tides are not strictly necessary, but they still might be important overall, right? So that all of these things need to be brought together, in order to sort of answer this question of overall how much of this heat transport is being done by tidal pumping as opposed to just sort of the normal salt wedge-like dynamics that you would get in such an estuary.
Have you done any, I mean, these millimeter scale turbulence computations are really fantastic. But how different would that scenario look if you actually put in the physical effect of tides at grounding lines, which is that presumably that gap is opening and closing on a daily cycle, and more drastically on the spring neap cycle. And I would have thought that having a piston that's going up and down is going to stir things up a lot more than the rather subtle fluid dynamics that you're looking at in those simulations.
Yeah, and I mean, the answer might be that what we've already looked at is a lower bound, right? Now, as far as changing the cavity geometry cyclically, that's going to be a challenge because you, at least with most current models at sort of these high fidelity models, can't do that sort of thing, and certainly not the one that we were using. There might be others that can, or that capability could be developed if somebody was really interested in that. The other way that you could potentially get at that without changing the cavity geometry would be to sort of impose a cyclical ocean velocity, right? Ocean kind of influx velocity. Whether that's the same thing as what tides are doing in terms of, pumping, I think is kind of an interesting question. But that is certainly something that could be done with the models that exist now. But yeah, the challenge with using these high fidelity models is that for the most part, they want to have fixed boundary conditions. And so doing the sort of thing that you said, I would love to do that. I would love to know the answer to that, but I think probably not possible right now.
Thank you.
Thanks a lot. Thank you both. Is there another question? Otherwise, this discussion makes me think that it's about a good time to move on to the second part of our session. So first, I want to thank you again, Alex, and thanks, Britney, for sharing your work and today. So as I said, we're going to move on to the second part of our session, and let's move on. And so the idea here is that